Right now, resting on corporate servers all over the world is an invisible graveyard. It is filled entirely with mathematically flawless, perfectly written code that is decaying into ash because no one is using it. Getting an executive team to sign off on an artificial intelligence project used to be the primary hurdle. Today, businesses are eager to invest. Pitching the concept is actually the easiest step in the entire process. So engineering teams retreat to their sandboxes. They train their algorithms, validate their datasets, and pop champagne when a predictive model hits 95% accuracy in a controlled environment. Then they export those brilliant predictions into a spreadsheet, email it to a busy operations manager, and wait. And nobody ever opens the file. The central bottleneck in technology has completely relocated. We have thoroughly mastered how to build algorithms that predict. The modern struggle is building systems that actually deliver. A mathematically perfect model sits at exactly $0 in real-world value until it successfully bridges the gap into a human action. Let's look at how this breaks down on the ground. Imagine a global logistics network fighting to keep supply chains moving through a congested harbor. A data science team swoops in and builds a spectacular solution. Their algorithm ingests weather patterns, analyzes shipment manifests, and historical port delays to accurately predict the exact minute the port will gridlock. To hand off this powerful insight, the engineers build a custom dashboard for the port dispatchers to use. That exact decision is the fatal error. Port dispatchers are already staring down 10 different screens, fielding radio calls and managing heavy machinery in real time. They lack the cognitive bandwidth to constantly refresh a secondary, standalone piece of software. The new dashboard stays minimized. The predictive insights sit entirely unseen. Hours later, the Harbour suffers a catastrophic backup, costing millions of dollars in delays, all while a perfect prediction of that exact event waits unread on a background tab. If you introduce even a tiny amount of friction into a worker's daily routine, you completely neutralize your own technological capability. Fixing this requires tearing down the wall between the build room and the operations floor. Engineers and dispatchers must sit at the exact same table to co-create the solution. Instead of building a new dashboard, the predictive insight has to be injected invisibly into the native dispatch software those operators already use. When a bottleneck is predicted, it should appear as a simple alert directly inside their standard checklist, giving them the option to reroute a massive cargo ship with a single click. Once the workflow is seamless, you have to prove it actually works. You use a concept called Uplift to measure true incrementality, casting if the model actually improved the outcome compared to normal human behavior. To find that number, you run a strict A/B test. As this chart shows, comparing a control group of standard dispatchers against the algorithm-assisted group reveals the exact numerical efficiency gained by your system. But algorithms will always encounter edge cases they cannot handle. You have to design a human-in-the-loop failsafe, an instant appeal path where an operator can manually override a strange routing suggestion. Proving a model's worth has nothing to do with quoting a high accuracy score from a test environment. It relies entirely on measuring actual behavioral change on the floor. It is dangerously easy to obsess over a specific piece of tech and fall in love with your proposed solution, rather than falling in love with the actual problem. We have to update what we consider a finished project. Deploying a piece of code to a server is an early technical milestone, but a human actually pressing a button is the finish line. True success requires achieving a permanent, measurable change in how an entire organization makes its decisions. The hard truth of data science is that writing the code and training the model represents about 20% of the effort. The remaining 80% is spent designing the human ecosystem required for that technology to survive. An algorithm only possesses the math to predict the future,